Okay, example 4s is to show that any two eigenvectors of this matrix that correspond to distinct eigenvalues are orthogonal. So I started out by taking the determinant of lambda I minus a. I get this characteristic polynomial, and notice at this point we have a difference of perfect squares. This squared minus this is actually 1 squared. So I can factor it as the square root of this plus that times the square root of that minus that. So we get lambda, let me zoom in, so we get lambda minus 2 times lambda minus 4. So we get our two eigenvalues when we set that equal to 0. Our lambda 1 equals 2, lambda 2 equals 4. Alright, so let's find the eigenvectors for those guys. So let's take 2i minus a. So 2 minus 3 down the main diagonal would be minus 1, minus 1. 0 minus the other minus 1s, or sorry, 0 minus the other ones give me minus 1. We reduce that, and you should get 1, 1 in the top row, 0, 0 in the bottom row. So we think about what eigenvector would we get here. x1, or sorry, x2 would be free, so x1 would be negative x2, so we get negative 1, positive 1 times some free variable s that's not equal to 0. And then for the other eigenvalue of 4, take 4i minus a. So I get 4 minus 3 in both main diagonal spots. Still have minus 1s over there and there. We reduce this, and I got 1, negative 1, 0, 0. Okay, so again, x2 is our free variable, x1 would be positive x2. So we get those eigenvectors. Alright, now we want to check that they're orthogonal to each other. To check if they're orthogonal, let's take their dot product. So I'm going to take x1 and dot it with x2. Let's see if this is true for all these. So if I distribute the s, this would be negative s, positive s. Oops, negative s, positive s. And this would be positive t, positive t. So if I dot these two, we get negative st plus st. Well, st and negative st are always going to add up to 0 no matter what s and t are. So since their dot product is 0, these two have to be orthogonal.